Continuing on in class 13 in fluid mechanics, here is an example out of Munson's book. Here is a stationary vane where we have a nozzle that is pushing water onto it, and we want to find out the anchoring force that's needed to hold the vane stationary if gravity and viscous effects are ignored. So, where is that? Let's see here. Boom. And we're going to assume a bunch of things. Let's assume that the area right here, which is given, is going to be the same as the area right there. It's a little bit of a weird thing. We'll like choose our control volume to be like something like this right here, and to be wrapped all the way around to this. And so we have a control surface here, and we have a control surface right there. So here's my assumes. A1 equals A2. And therefore V1 is equal to V2. So we're also assuming that it's incompressible, which is basically, we do that all the time. We're also going to assume that beta, which is used in the Sengel book, but not used in this book, is going to be equal to 1, or is approximately 1. That's a good enough assumption. We're going to take our mass flow. We can find that by taking the density times the velocity times the area, which are given right there. So the velocity they're saying is going to be 10 feet per second. Let's see, also this is going to be water, so 1.94, 10 feet per second, and the area is 0.06. So we're going to end up with 1.164 slugs per second. And the FBD, let's see, I'll draw out this thing first. Let's see if I can make it look a little bit like the thing. Not quite. So here's my control surfaces, and here's my FBD of the piece. And they said to ignore the gravity, so I'll draw the weights in here, though. We get the weight coming down. We have the reaction here. We can call that normal force if we wanted to. And we don't necessarily know the direction of the reaction, so let's go ahead and put it to the right, because that's what I'm going to decide is my positive right here. And we're going to set that equal to, try to draw the same thing again. No, I'm not doing a great job of it. There we go. So here you go. Here's our control volume, and here's our control surfaces. And so this is, I'm going to call this my momentum diagram. And so we're going to have fluids crossing these control surfaces, m dot V1. We're also going to have m dot V2 right here. You'll notice that this is going at an angle, but we don't know that angle right there. Right? We're not given that angle. So we're not going to be able to solve this for a particular value, but we can do it for a range and then find out what that ends up being. So the main equation that we're using is the sum of the forces on the control volume are going to be equal to the sum of the beta times m dots times velocities on the outgoing, on the out control surfaces is going to be equal to the sum of the in. You get the beta m dot there. So this is our main equation that we're going to go to, and in the x direction, we end up seeing that we're going to have now we don't have any pressures acting onto here because this is from the nature of the problem. You can see that this is going to be atmospheric pressure right here. So and there's none up here either. So there's nothing acting in the x direction except for the reactions. And so over here, we're going to take for the outlets, we're going to go beta m dot V1. I'm sorry. It should be V2, right? Because we need the outlets. Oops, outlets. And so that's going to be the cosine of theta for right there. Minus beta m dot, and then v1. So Rx, we put a value of 1 here. We found this is 1.164. This is the same as that right there. It's 10. And times the cosine of theta. And we get all the same things here, right? So beta is 1, we're assuming. M dot is 1.164. And V1 is 10. So we're going to have an equation here. That's going to be 11.64, and it's going to be cosine theta minus 1. And our y direction. Ry, we're going to ignore the weights. We're saying that they're negligible. Or negligent, I don't know which. And this will be only going to be the outlet. So m dot, well, let's put the beta in there just for lip service. V2 sine of theta, which is going to end up being 1 times 1.164, 10 times the sine of theta. Therefore, our Ry is equal to 11.64 times the sine of theta. And we can graph this. And let's see, let's go for 180 degrees, 90. Here's some 45s for you. 135, whoops. So here, this is going to be a positive value, and this is always going to be a negative value because that's always going to be something less than 1, or it's going to be equal to 1. And this is really coming up to 11.64, and it's going to be a negative 11.64. And so up here at the top we'll have Ry, here's going to be Rx, and we're going to see this is going to go up wee, right? And it's going to peak out right there. And then let's see if we can have this one right here. Okay, so this is going to be like that right there, right? So you can see that like we're going to actually have the maximum amount of this reaction in the x direction. When we have like a nozzle that looks like something like this right here, right? Where we get the stream and it comes in all the way, right? So we know that's not necessarily going to be perfect along those lines. And one aspect I thought that was very a weird assumption to make, but we're probably trying to make it. Where we see the determine the anchoring force needed to hold the thing in place. This guy right here made that assumption that the flow wouldn't like change around, that it would remain a circle. But maybe I guess that's not exactly right. Maybe it turns out to be a flattened or something on there, but it's still going to get this flow back. Maybe it would disperse out to the side or something like that. They get some losses going on. But anyway, this is problem out of Munson, and it only took me 8.5 minutes. Is there enough time? Could I do the other problem, or I'll just make it a second video? All right, so more videos are better. So we'll continue this on with video 4.